Ever wondered about those hidden forces? You know, the ones that kind of make our world tick? I'm talking about those silent chemical reactions, the ones happening everywhere, even inside us.
Yeah, it's like this hidden dance of energy, constantly shifting, reshaping our reality.
And today we're going to try to peel back the curtain on one of these invisible forces. Oxidation and reduction reactions. Ready to geek out a bit?
Absolutely. These reactions are everywhere. I mean, think about it. The rust on that old bike, the battery keeping your phone alive, we're practically swimming in them.
And for this deep dive, we're going straight to the source. We're talking Professor Pedro Camargo's Inorganic Chemistry lectures. He's over at the University of Helsinki, so think of this as a backstage pass to the world of electrons.
He's brilliant.
Professor Camargo starts things off simple. He says oxidation is basically when something loses electrons, and reduction is when something gains them.
It's like a dance, right? You can't have one without the other. One partner loses an electron, the other swoops in, grabs it, boom.
Yeah.
Redox reaction.
So it's like a never-ending electron hot potato.
Exactly.
Oh.
And Professor Camargo uses the example of, well, I'm sure you've got it in your pocket right now, a lithium-ion battery.
Okay, so let's break that down. What's actually happening inside that battery every time we charge our phones?
Picture this. Tiny lithium ions. They're zipping through the battery from one electrode to the other. And during this little trip, they lose electrons. And that's oxidation in action.
So these lithium ions are like tiny delivery trucks just dropping off electrons along the way.
You got it. And then at the other end, you've got other lithium ions picking up those very same electrons.
Yeah.
That's reduction. They're grabbing those electrons and, gaining a little something in the process.
And this whole electron swap meet, that's what creates the electrical current that powers our phones. It's like a tiny city powered by these invisible exchanges. Mind-blowing.
Isn't it? And get this. This basic principle, this electron transfer, this redox dance, it's behind tons of other processes. It's how rust forms, how plants make energy from sunlight, even how we break down food.
Wow.
It's wild.
So we've got oxidation and reduction happening constantly, always balancing each other out. But how do chemists even keep track of all those electrons? Seems like it'd be easy to get lost in the electron shuffle.
Oh, it would be chaos. But luckily, chemists are a clever bunch. They came up with this handy tool. They call it, are you ready for it? Oxidation numbers. Keeps things organized.
Oxidation numbers. Okay, is this where it starts getting complicated?
Not at all. Think of them like labels, little labels that we stick on elements in a chemical compound. They tell us how many electrons an element has gained or lost, compared to its neutral state. Kind of like keeping score in a game.
So if an element loses electrons in a reaction, its oxidation number, it goes up.
Exactly. Like scoring points, the more electrons you lose, the higher your score. And the opposite is true too. Gain electrons. Oxidation number goes down.
Okay, that makes sense. So just by looking at these oxidation numbers, we can tell which elements have been oxidized and which have been reduced, like a chemical detective story.
Precisely. And these numbers aren't just for show. They actually help us understand why some elements act in predictable ways. You see, some elements are like, well, they're like electron hoarders. They always want more, always trying to snatch them from others. Those are our strong oxidizing agents.
And then you have the elements that are more like electron sharers, right?
Exactly. They're more likely to get up electrons. Those are our reducing agents.
Okay, this is starting to come together. So we've got these electron givers and takers, always interacting, always shaping the world around us. But how do we know which ones are going to win this electron tug of war? Is there like an electron popularity contest happening at the atomic level?
Uh-huh. You could say that.
Yeah.
And every good competition needs a ranking system. In chemistry, we call that reduction potential, which we show with the symbol E degree.
Reduction potential, so the higher the E degrees, the more an element really wants those electrons.
Exactly. Think of it as an element, like electron pulling power. High E degrees. They're like the friend who always steals the spotlight. They just have this strong attraction. Low E degrees. Not so much. They're happy to let others have the limelight.
So is there like a leaderboard for this? Like a who's who of electron magnets?
There is. It's called the electrochemical series, and it ranks all the elements based on their standard reduction potentials.
No.
Right at the top. The strongest oxidizing agents are the electron magnets. And as you go down the list, you get to the strongest reducing agents, the ones practically giving their electrons away.
So this electrochemical series is basically a cheat sheet for predicting how elements will react, right?
It is. You look at two elements on the list, look at their positions relative to one another, and boom!
Yeah.
You can predict if a reaction will just happen spontaneously. like a ball rolling downhill. It's a chemist's crystal ball.
So I can look at this list and say, okay, these two, total electron frenzy. Those two, not a chance.
Exactly. And knowing this is huge. It's how we design better batteries. It helps us understand how pollutants react in the environment. But keep in mind, this is all happening under what chemists call standard conditions, which basically means a perfect world, 25 degrees Celsius, everything perfectly dissolved.
But the real world, it's a little messier than that, isn't it?
Oh, absolutely. In reality, all sorts of things can influence these reactions. Temperature, how concentrated things are, even the pH, and that's where things get really interesting. To help visualize these complex interactions, chemists have come up with some pretty cool tools. Diagrams. They basically map out this intricate dance of electrons.
Diagrams, huh? I'm all ears, or should I say eyes. I'm a visual learner, so this
Yeah.
is right up my alley.
Well, one of the most common ones is called a Latimer diagram. It's basically like, imagine a clothesline, right? But instead of socks, we're hanging all the different forms of an element on it. Each one represents a different oxidation state.
Okay, I'm picturing it, so like different versions of the same element, just depending on how many electrons they've gained or lost.
Exactly. And the cool part is we write the standard potential for each transformation, right on the line that connects them. So you can see at a glance how easily that element, flips between those different forms.
So clever. It's like a family portrait. Shows you all the different faces an element can wear.
And speaking of family portraits, there's another diagram we use. It's called a Frost diagram. It's a bit more, well, abstract.
All right, I'm game. Lay it on me.
So picture this, a line graph.
Okay.
Okay, on one axis, we've got the oxidation number. Remember, that's our electron scorecard. And then on the other axis, we have energy. The steeper the line, the line connecting 2 points, well, that tells you how strong the drive is for that transformation, whether it's
Yeah.
grabbing electrons or giving them away.
So steep slopes, those equal big dramatic transformations, kind of like those reality TV families. Always some drama going on.
You got it. And remember we were talking about iron rusting earlier?
Yeah.
Well, there's a diagram for that too. It's called a pore bay diagram. And it's like a roadmap for redox reactions in water.
Okay, so this is where things get like really practical.
Exactly. These diagrams show us which forms of an element are stable under different conditions. So think about it. You've got pH on one side and potential on the other. It's a grid. And depending on where you land on that grid, your iron could be hanging out as a dissolved ion, or it could be busy forming rust on your car.
So these diagrams help us understand like why some metals corrode in some environments, but not others. That's incredibly useful.
Exactly. And it's not just for metals. These pore bay diagrams are essential. I mean, we use them for all sorts of things, like understanding what happens to pollutants in water, or even, the availability of nutrients for plants.
We've covered so much ground. It's just amazing to me how these, I don't know, these seemingly basic ideas, losing and gaining electrons, they have such a huge impact on, well, everything.
It really is incredible. But there's another layer to this whole chemical onion.
Ooh, I'm intrigued. Tell me more.
So we've talked about the direction of these reactions. Will they happen or won't they? But what about the speed? Just because a reaction can happen, that doesn't mean it will happen, quickly.
That's a really good point. I mean, think about it. Rust forming on a car, that takes a while. But a battery, that powers up in a flash.
Exactly. And that's where reaction rates come in.
So some oxidation and reduction reactions are like lightning fast, and others are more of a slow burn.
Think about how much faster, like, if you're dissolving sugar, right?
Yeah.
How much faster does it dissolve in hot tea compared to iced tea?
Yeah,
Heat speeds things up. Increasing the temperature usually makes reactions go faster.
makes sense. And I'm guessing if you have more reactants, more stuff in the mix, that would also make the reaction go faster, like having more dancers on a crowded dance floor, just more chances for collisions and connections.
Exactly. And just like a good dance, sometimes you need a catalyst to really get things going. Catalysts are just substances that, well, they make a reaction go faster, but they don't get used up in the process.
So they're like the matchmakers of the chemical world, bringing reactants together.
I like that. They're like creating those connections. What they really do is they provide an alternate route for the reaction to happen, one that takes less energy.
Like taking the express lane on a chemical highway?
Exactly. So it's not just about if a reaction will happen, but how fast it'll happen.
A delicate balancing act.
And chemists are always trying to find that sweet spot. Think about drug development, right? It's not enough to just make a drug that will, bind to something in the body. It also has to happen at a rate that actually makes a difference therapeutically.
It's like finding the perfect tempo for that chemical dance.
Precisely. And this whole idea of reaction rates, it's essential for so many things. Developing new energy technologies, creating more efficient industrial processes, it's huge.
Okay, so we talked about diagrams, reaction rates, I mean, really the whole shebang. But I want to go back to something you mentioned earlier, those lithium-ion batteries, the ones we all have in our phones. You said that during discharge, those lithium ions, they flow back to the other electrode, and that reverses the process, which powers our devices. But how do they move so fast through the battery? It's not like they're swimming.
You're right, they're not swimming. The material between the electrodes, we call it the electrolyte, that's what makes it all possible.
So it's like a superhighway for those lithium ions.
Exactly. And what's really cool is that the nature of that electrolyte, whether it's a liquid, a gel, even a solid, that has a huge impact on how well the battery performs.
I bet that's where the chemistry gets real part comes in, right? Like
Yeah.
designing that perfect electrolyte highway sounds tricky.
It is, but that's what makes it so fascinating.
So we've got all these scientists out there trying to create the perfect, the ultimate electrolyte, right? To get those lithium ions moving.
It's true. They're experimenting with all sorts of materials, liquids, gels, even solid electrolytes. It's all about finding that balance, conductivity and stability. Like designing a highway, but it's got to be super fast and indestructible.
So the next time I charge my phone, I'm going to picture all those tiny lithium ions racing around on their little highway, powering all my scrolling.
It's pretty amazing when you think about it.
Yeah.
And it all comes back to those fundamental ideas we've been talking about, oxidation, reduction.
This whole deep dive has been, I don't know, it's been eye-opening. I feel like I have a whole new appreciation for, the chemistry that's happening all around us all the time.
That's what we like to hear. And hopefully this is just the beginning. We've only scratched the surface of these reactions, and they're everywhere.
It's true. I'm already thinking about those catalysts. What else can we, speed up with those chemical matchmakers?
Oh, the possibilities are, well, they're pretty much endless.
Yeah.
But I think that's a topic for another deep dive.
Well said. And for our listeners, if you want to keep going down this rabbit hole, we've got links to Professor Camargo's lectures in the show notes, along with tons of other resources. It's a whole library just waiting to be explored.
Absolutely.
In the meantime, keep those brains buzzing. And remember, even the most, the most everyday things, well, they can be extraordinary when you understand the chemistry behind them.
Couldn't agree more.
Until next time, keep exploring. We'll catch you on our next deep dive.